Okay, so ladies and gentlemen, dear colleagues, I'm very happy to see you here. Let me start the first seminar of the series, which is called Scheduling Seminar, right? First of all, let me say a few words about the objectives and organization of the seminar, and then we will have the talk. So Mike Pinedo, Guohua 1, and I believe that it is the right time to improve our collective learning, especially in these difficult COVID times. So in contrast to traditional papers, such a seminar might help us to capture charisma and enthusiasm of the best researchers. And this is definitely an example to follow for, let's say, us and younger generations. So we want to attract young people, namely, and we want to convey them know-how and information about our domain in the way which is easy to understand and which is modern and which is attractive. So we expect the seminar to be every second Wednesday. The talk should report on work which was already maybe published and which went already through the review process and which is mature in some sense. And it may cover both hot topics and breakthroughs and also surveys of traditional results. We should pay equal attention to the theory and applications, since nothing is more practical than well-applied theory, right? So let me go further. The quality of the seminar is given by the quality of the speaker, and therefore we put in place a large program committee, and this committee will help and be in charge of choosing the best talks, and eventually will cover all geographic areas and all subdisciplines and special flavors of scheduling, right? The respective co-chair will be in charge of introducing the speaker and recording the talk. So if you miss the talk, you still have a possibility to follow it on YouTube offline. After some time, we expect to have like a nice collection of talks on YouTube. And we have ambition to compete with Netflix and Hollywood filmmakers, so that finally every little child can understand at least our ILP formulations, at least a little bit, right? If you are a student and you are interested to do your PhD in scheduling, then believe us that you can advance theory and this theory can be applied in nice applications. But either way you do it, you will stand on the shoulders of giants. Some of those giants are on the screen now, and many other will give their talk in the seminar. I still have to admit other people, right? And now, if you want to ask questions, please go to Slido and enter code 141421, the first 6 digits of a square root of 2. And there you can enter your questions. And these questions possibly will be answered. We don't know how many of them there will be, but we will manage them in some way and display them to speakers at the end of their talk. And now let me ask Guohua to introduce himself and Mike to introduce himself and speakers. And if anybody of you needs to share your screen, you can do it now. Okay.
Thank you, Zdenek. It's my honor to join this committee for coordinating this series of seminars. As Zdenek just stated, our objective is to popularize and also attract more people to join our community. So it's my pleasure to see so many friends on this platform, and I expect the success of this series of seminars. So my name is Guohua Wan. I'm from Shanghai Jiao University in China. So my research interest is basically in applications of scheduling theory in various areas, including supply chain and healthcare operations. So I will try my best to organize people in Asia and Oceania to join the seminar and to help the success of the seminar. Thank you very much.
Okay, Mike, it's your turn, but you have disabled mic. Okay. But it's not so easy to find one person among 250. It's still jumping up and down. Oh my goodness. Ah, here you are. It's a little bit slow.
Okay.
Okay.
Sorry about that. Let me introduce the two speakers, Jan-Karel Lenstra and David Shmoys. Let me tell you, I know Jan-Karel from 1977, 1978, and this is a Berkeley connection that all of you know Jan-Karel Lenstra from. He put a structure on the deterministic scaling theory field. All of you know his notation and his classification of scaling problems. Without them, actually, we would be lost because it was so many scaling problems. He really put a structure on the field. At that time, so he was the master already in the 70s. And David Shmoys and I were PhD students then. I may have been a little bit older than David, but we were just following the master. I'm from a stochastic and David from a traveling salesman. We were learning from him. David became, of course, very famous on his own right, and you are going to hear from him later on. Okay, so now you meet Jan-Karel. He is the author, the co-author of that very famous paper that presented the notation and classification of scheduling models for all us researchers to work on. Okay, Jan-Karel, please go ahead.
Okay, there we are. Thank you, Mike. Well, it's a great idea of the three of you to start this online seminar and to keep the scheduling community together in these unusual times. And it's an honor that you've asked David and me to kick off this first installment. So, good afternoon, good morning, good evening, wherever you are. I will give a personal reflection on the early history of scheduling theory. And then David will take over and discuss the current paradigms in modeling and solving scheduling problems. So here we go. Why doesn't this work? I want to...
If you type page down.
Page down, I want to page down.
System administrator is coming, be patient.
The boss is coming.
Sorry, I'm sorry, but I don't know how to make this page down work.
Maybe.
There we are, now it works, fine. No, that is good. So we're in business. Okay, fine. Let me see if it still works. Yes. So you all know the book by Mike Pinedo, and to the left on the frontispiece, Mike shows Gantt, the inventor of the Gantt chart and the pioneer of industrial engineering. And I'm going to show you my heroes of the early days of the theory of scheduling. And the first one, of course, is Selmer Johnson, who solved the two-machine flow shop essentially by sorting. What you perhaps don't know is that he also was co-author with George Danzig and Ray Fulkerson on a paper in which they solved a 42-city TSP, which was quite a remarkable feat at the time, by solving an LP relaxation and adding hand-generated cuts. It was the first paper on polyhedral combinatorics. And he also later indicated how to generate all permutations of a finite set by adjacent transpositions. Johnson was in fact a pioneer of combinatorial computing. Now my second hero can be no one else than Wayne Smith of the SPT rule and the ratio rule for single machine scheduling. That's a very famous paper. Smith also indicated how to meet deadlines, how to handle deadlines for those problems, which, however, only works in the unweighted case, but we forgive him. At the summer school that we organized in Durham in 1981 on deterministic and stochastic scheduling, Smith's rule was cited in almost every lecture. So we wanted Smith to appear on the group picture. And Gene Lawler located Smith at UCLA. Smith got a haircut, sent his photograph, and we put him up in the tree. There you see Smith on our group picture. And these are the participants. Here you see Mike Pinedo. There you see Gene Lawler, Chris Potts, Rolf Meuring, Marshall Fisher, all those famous people over there, but all under the guidance of Wayne Smith. Now I'll talk about the 70s, about the elements that we started from half a century ago. The main body of work at that time was in OR. You had results for single machine scheduling, flow shops and job shops. But you know, you had a simple rule, an elegant rule for the two-machine flow shop, and for the three-machine flow shop, you had to resort to lame heuristics or clumsy branch and bound, and no one asked why. It was just a fact of life. And Alexander and I, we set out to compile the state of the art, and our organizing principle was this classification scheme of Conway, Maxwell, and Miller for queuing and scheduling problems. We soon discovered parallel work, independent work in computer science, single machine, parallel machine models motivated by the control of computer systems. And in May 1973, Michael Florian of the Université de Montréal, he visited the Math Center in Amsterdam, and we talked, and he saw that I was intrigued by relations between problem types, like linear assignment is relaxation of the traveling salesman problem, traveling salesman is a special case of quadratic assignment, and so on. And he then said, you would like this paper I saw, this reusability paper of Descartes. Wow, that was quite a discovery. That became our second organizing principle, the complexity theory of Cook and Karp, which meant a revolution in computational science and which allowed us to bring order in the scheduling chaos. We slowly became aware, perhaps too slowly, of a third strand of work in mathematics. Graham's multiprocessing anomalies, or what we now call performance-bound for list scheduling and LPT scheduling on identical parallel machines, work that predates complexity theory. So those were the elements that we started from, and major events for Alexander and me at that time were a number of conferences in the mid-70s, where we saw that what other people were doing and which helped us to define our position in the community. The first of these was a summer school organized by Bernard Roy in France, a NATO school. This was a bilingual meeting. It was very strange. Half of the people were giving lectures in French, the other one in English, and they each part understood about 50%. So they were essentially two separate meetings that happened to coincide in time and space. And Jean Lawler, we met Jean Lawler there. He had to talk about his work on the quadratic assignment problem, but after hours, he gave an illicit talk on computational complexity. And Jean, Alex, and I shared a common ground in scheduling and complexity, which was rare at the time. And immediately the three of us planned to write a book after Alex and I had gotten our PhDs. And then a year later, there was this fantastic workshop on interactive programming organized by Bernard Cote. I remember that one of the funding organizers, IBM, insisted on serving bottles of wine of 60 D-mark at the conference dinner. I think that Versailles and Bonn contributed a lot to shaping the emerging discipline of combinatorial optimization. Alex presented our complexity results with Peter Brooker at that meeting, and afterwards Dick Karp and Jean Lawler visited the Math Center in Amsterdam. Our old building was located next to the Amstel Brewery, and in the hallways you smelled the smell of stale beer and jammed Xerox machines. And in my old dingy office, Dick and Jean and Ben Lagerweg and we started a project, a fun project. We had over 4,000 problem types in scheduling. We had a natural partial order defined on them. I mean, job shop is more general than flow shop, and release dates are more general than no release dates. And with this, we generated random change in scheduling space, moving from easy to open to hard. And Ben overnight wrote a program, MSP class, which determined the status of each problem, and also computed the problems that were maximal easy, minimal hard, and so on. And in the succeeding fall, we knocked off many targets of opportunity. And at the end, in January 76, we presented a nice hardbound complete listing to Alex, when he defended his PhD in January. So MSP class was later maintained by Sigrid Knoest in Osnabrück, and I think now by Christophe Dur in Paris. And then just after Alex defended his PhD, and a few weeks before I did, there was this scheduling conference in Orlando, in Florida, organized by Tom Hodgson and Don Radcliffe, a meeting point of OR and computer science. Marshall Fisher presented his Lagrangian relaxation lower bound for single machine scheduling. Ed Kaufman, Mike Gary, and Dave Johnson, their bin packing upper bound for multiprocessor scheduling. And it was sort of a collision of cultures. Someone would present another well-solvable case of the three-machine flow shop and then happily announce that he was well on track in solving the three-machine flow shop as a concatenation of special cases, after which David Johnson would get up and explain that this research program was unlikely to be successful in view of the insights offered by complexity theory. 2 months later at Carnegie Mellon, there was a computer science meeting on algorithmic complexity. Dick Karp presented his probabilistic analysis of traveling salesmen and set covering problems. And Nikos Christophidis presented his famous 3/2 approximation rule for the TSP with a triangle inequality there. He was spending a sabbatical at Carnegie Mellon with Egon Ballas, and he thought of taking a minimum spanning tree, which is the one, plus a matching on its odd degree vertices, which is the half. And you know, Dick Karp told me at that meeting that he also saw the algorithm, but he failed to see the half. And this is still the best we can do, essentially, 3/2. However, Nichols never published it. And I asked him why. And he said, well, when I got back to London, my boss told me, Nichols, at Imperial College, we do practical operational research and no useless math. So that was the end of the paper. Nichols became a pioneer in vehicle routing, using lots of useless math, and later moved to the more profitable field of financial mathematics. That summer of '76, Peter Hammer asked us to present surveys on complexity and scaling at a symposium that was going to take place in Canada, Discrete Optimization 77. And then Alexander and I decided to completely overhaul the classification system. So the job shop NMGCMax became simply JCMax. And one of the best recollections I have of that period is a summer school in Italy in the spring of '77, organized by Nichols, Aristide Mingozzi, and Paolo Todd, where next to enjoying the lectures and the Italian food and the Italian wine and the Apennine Mountains, I compiled our scheduling survey, merging the drafts provided by Ron and Jean and Alex. Let me see, where are we? So this scheduling survey summarized all that was known to us about this segment of the universe. And it meant sort of the end of adolescence of scheduling theory and perhaps also of ourselves. This survey has collected more citations than there are problems in MSP class. It was updated for our Durham Summer School in '81 without Ron Graham. And then it was completely rewritten for the handbooks in OR and Management Science with David Shmoys in the fall of '88 at MIT. And that's the best version that we produced. These are the elements of scheduling that we intended to cover in our scheduling book. Now, at the Mathematical Programming Symposium in Amsterdam in August '91, we made a bet with the three Bills and Lex, whose manuscript would go to the publisher first. And here's his bet. Here you see the three Bills and Lex, and here are the four of us, August '91, signed by Lex and me, manuscript to publisher for one Indonesian rice table, and the bet has never been paid off. We lost. Their book was published in '98, and ours never came to be for many reasons. However, we do have 2/3 of a book written by 11 people, and we put it on the web. So please have a look at elementsofscheduling.nl and feel free to use these elements in the classroom. These are the contents, and the shades of gray suggest the status of the chapters. There are 6 complete chapters with which I'm pretty happy, 2 non-existing chapters and 6 other chapters there at various stages in between. I'm working on updating all this material to make it even a little bit less bad than it is right now, which will be done in the summer. And we do have a cover of the book with this nice painting of the job shop problem by Emil Arts, which is down the hallway here in this house, and all the authors that contributed to this non-existing book. So a brief intermezzo. This is Jean Lawler, my mentor and friend for 20 years, the author of the famous book on networks and matroids, and the driving force of scheduling theory until he died in 1994. His primary interest was in efficient optimization, in polynomial, pseudo-polynomial time, and he was the wizard of dynamic programming recursions. And when Jean was the algorithm designer on the team, then I have to admit to a destructive tendency in myself, in the sense that impossibility results appeal to me. What I like in particular is the NP-completeness of finding a short schedule of integral length, since that excludes the existence of a good approximation method. For example, finding a shop schedule of length 4 is hard. So it's unlikely that you can guarantee to come within 25% of the optimum polynomial time. Now, this slide is only an excuse to mention some of the great colleagues with whom I've had the privilege to work: Alexander, David, Eva, the other David, Leslie, Han, Cor, Sergey, and many more people. And when I'm the pessimist looking for impossibilities, Alexander Rinoy-Kan was the optimist, as is shown by the bet that he made with Jean much earlier in '77. He claimed that the P versus NP question would have been settled in 12 years. And he lost 12 bottles of champagne on that, 1 bottle for each year. Yeah, back to alpha, beta, gamma. Alpha, beta, gamma is useful as a shorthand notation, and it brought organizational clarity in the scheduling jungle. And it is probably our own fault that it also became to be seen as a research program in itself. While many of the alpha, beta, gamma problems are not for real and only exist because they have been generated by a computer program. And I have to admit that at one point this kind of self-generating aspect of our field started to worry me a bit, but I'm happy to observe that you have stepped across this pitfall. I see a mature and healthy area which is practically relevant and scientifically challenging, and it has developed way beyond my comprehension and capabilities. So here's my final slide. I would like to put as a challenge to you the analysis of the methods that are being used in practice, as opposed to the methods that have been designed to have good performance bounds. For example, explain why local search is doing so well, and explain why for jobs of scheduling constraint programming is so much more effective than integer linear programming. There is a gap between what we do and what we understand. And next, there are new paradigms, new ways to think about scheduling problems, like online algorithms to address uncertainty, and learning from data to account for the diversity of input. But now I am entering David's territory and I stop. David, over to you.
Thank you, Jan-Carel. So let's hope the technology works.
If you're interested, you can ask questions over Slido. 141421 is the passcode. And we will also unmute participants. Now we have like 44 participants, but we are a little bit afraid of unmuting you because there could be a lot of noise. So especially if you have started YouTube and Zoom at the same time, then there is a danger that we will recursively record it in YouTube, right? So after the talk, there will be questions, and then I will unmute everybody.
Okay, so Jan-Carel, thank you very much for this nice retrospective. I think what I would like to do in my share of the talk, though I'm now also suffering from technical problems, is to look forward a little bit. That I will take issue with Michael Pinedo. I was not a PhD student in the 70s. I was a PhD student in the 80s. I like to joke with Jan-Carel that when the scheduling book was conceived, I was still in junior high school. So and what I want to talk about is mostly a small subset of results that I find particularly nice of others that I think set the tone for the evolution of the interplay between theory and practice for modern scheduling. So if one thinks about data-driven scheduling and resource allocation more broadly than scheduling itself, there are just a host of places that young Carl alluded to the fact that some of the early days of scheduling were driven by, models for computer scheduling. But it only, takes a moment to look back on that past to know that that was a promise that was largely unfulfilled. It was not that these were scheduling problems that gave rise to a large gamut of implemented algorithms in that context. But in the next generation and in the present, we see great more integration of scheduling problems at scale that are being addressed by really truly interesting algorithmic developments. One only has to think about the way in which cloud computing is run, both from a scheduling and a resource allocation, or even just within data center management in terms of scheduling traffic and networks, or going a little bit more broadly in terms of resource allocation. If you think about the rideshare enterprise and how resources are allocated both by incentive and explicit decisions. And another piece of this that young Carl mentioned is that really one of the most important aspects that we're still wrestling with, and we've wrestled with for years, is sort of models of an unknown future. And in some sense, there have been two traditions within the scheduling community to do this, in many ways marking the split between the probabilistic and the deterministic worlds. That if we think about the traditions of online analysis, and online analysis, there are two main threads within scheduling. There are arrivals of jobs over time, and there's what's often been characterized as the split between clairvoyance and non-clairvoyance in terms of, do we know the processing requirement of a job when it arrives? And these are, there's a long tradition of viewing these problems from a worst case viewpoint. And in contrast to that, there are stochastic models, queuing models for arrivals, probabilistic statements of resource requirements, and then analyzed from the perspective of average case performance, or perhaps performance with high probability. Now, I'll make one sort of judgment call that if I think about those two threads of research, in many ways, online analysis is often been too pessimistic, and as a result leads to algorithms which are designed to thwart an unknown adversary. And stochastic models may often be too optimistic and may reveal more about the underlying probabilistic assumptions than about scheduling in practice. Now, I want to start with a very simple example. One in many ways already alluded to by young Carl, and sort of put that in perspective of what those two threads of research have long known. And that's just scheduling a single machine with preemption so as to minimize the average completion time. So from an offline perspective, if I know all the data in advance, young Carl already mentioned Smith and the shortest processing time rule, this gives us an optimal schedule offline. But suppose that the processing time is revealed only by running the job. So stochastic analysis gives us one way to handle this problem, where we think about each job having a random variable that specifies its processing time, PJ, maybe let's say with an increasing completion rate. And as we process it, we can think of this, what's happening as a realization of the random variable. And it's well known that the optimal policy is to schedule in non-decreasing order in terms of the expected value of that random variable. In contrast to that, if you think about non-clairvoyant analysis, again, each job has an unknown processing time, but now we think about an adversary that determines the processing times, possibly knowing the algorithm. But let's say if it's a randomized algorithm, not knowing the random coin tosses of the algorithm to really give the power of randomization to the algorithm. Well, in this case, the best thing to do is sort of a very quickly cycling round robin algorithm that gives each job its own time in the sun in a cycle, and cycles around until the job completes. And it's known that this is comes within a factor of 2 asymptotically of optimal, a so-called 2 competitive algorithm. And it's also known that no better, whoops, that should have been for C equals less than 2, no randomized even C competitive algorithm exists as long as C is smaller than 2. So no better algorithm exists. So in a recent paper, Kumar, Purit, and Svitkina really showed that we can sort of blend the world of machine learning and as a bridge between the stochastic and the deterministic world. Because imagine that I had a mechanism to predict the processing times, that I have this set of jobs and I can look at their characteristics, who sent it to me or whatever, and I have some mechanism for making the prediction of what that processing time is. Well, in such a case, I've just modeled away the distinction between online and offline in the sense that it's another, in some sense, form of clairvoyance. But machine learning models may provide a mechanism in many settings to do that, but the predictions may be noisy or worse. So in this case, again, a simple algorithm might be to use the shortest predicted processing time. And of course, that works well if the predictions are, that works optimally, if the predictions are perfect, but it can be arbitrarily bad if the predictions are horrendous. So one question is, how can we build an algorithm that hedges against inaccurate predictions? So the very elegant result says, well, let's at least bound the performance of the shortest predicted processing time as a function of the prediction error. So let M, kind of unconventionally for this audience, be the total prediction error for an input with n jobs. So a rather simple and straightforward analysis, but very clean, can show that that algorithm comes within a factor of 1 plus 2m over n of the optimal solution. Now, so what that shows very explicitly, and this bound is tight, is that as m goes to infinity, this becomes arbitrarily bad. On the other hand, if the forecasts are perfect, if m is equal to 0, then it's one competitive. It is again, we get the optimality out of that. So one way that we can think about this is that rather than thinking about preemptions, we can think about preemptions as being a mechanism, and in some sense, round robin already is this, as a mechanism for processor sharing. We can think about what fraction of the machine's capacity is dedicated to running a schedule one way versus running a schedule the other way. And so we can do this shuttling back and forth between the shortest predicted processing time and round robin. And if I take an alpha fraction of the time to run the former algorithm and a 1 minus alpha fraction to run round robin, and then set alpha so as to exactly balance the two, we end up with a constant competitive algorithm in as a result. And so we're able to beat the worst case performance in many settings in this way. So that's one example where we're using our ability to forecast and yet hedge against the fact that those forecasts may be unknown. And I want to turn to a much more intricate example, which goes to a more general version of a model that Giancarlo already referred to, that of scheduling unrelated machines to minimize the make span. I want to now consider it in an online setting that is the job arrival, that mimics the job arrivals, but yet when a job arrives, we know all of its requirements. Now, I'm not going to consider the fully unrelated machine model. I'm going to consider the special case where when a job arrives, it has a processing requirement PJ, but it only can be processed on feasibly on a subset of machines, and which subset it can be processed on is specified upon arrival. Now in the offline, without release date setting, this is something for which we know how to use a linear program to obtain an offline to approximation algorithm. But in this online setting, Azarnar and Ram showed a log M approximation algorithm, or log M a competitive algorithm, and also proved that no online algorithm can have better competitive ratio. And the insight that Latanzi et al. Gave is that we can make use of very succinct and actually learnable predictions about the input, that it's more sophisticated than just the input data itself, and make use of that data to get a improved result in terms of the competitive ratio. So the predicted quantity in this case is not one of the input data. It's going to be a weight for each machine I. And the weights, again, can be learned by the online algorithm. Because I don't want to, I mean, one prediction I could make is I could predict on which machine I should be scheduling each job. But this is just something that's machine dependent and will be for each way. And it essentially says really how tight the competition is for access to that machine. How flexible is that machine as one thinks about the generic input? So the result works as follows, that first, the algorithm computes an online fractional assignment. Normally in this job, we think of for each job it being assigned to one machine or another. And as a measure of how correct the predictions of these weights are, I'm going to let R be the maximum ratio between, and I haven't even indicated what correctness means here, but the ratio of the corrected weight of the correct weight to the predicted weight. So again, a measure of how good our predictions are. And if I take that then as a metric of how good the input is, this fractional assignment comes within a log R factor of the optimal fractional assignment. So we're achieving something, well, that's a function of the guarantee. And I probably should have said log of O of R, because I mean, if R is 1, it's still only, it cannot be better than optimal. And the intuition, as I said, for the weights is and how they come into use is that the fraction of the job J assigned to machine I is simply the ratio of that machine's weight to the total weight of the jobs that are feasible for that job. So every job has a feasible subset of machines. And as I think about that fraction, and so this is a easily implementable online algorithm that computes an online fractional assignment. Again, but what we need the right weights. Secondarily to that, as I think about the fractional assignment, we can round a fractional assignment to an integer one, to a 0-1 assignment. And in so doing, use a logarithmic factor, log m, where m now is the number of machines cubed. And this is a randomized algorithm, and it achieves this makespan, not just in expectation, but with high probability. And then sort of the punchline beyond that is that we can prove that there exist weights for which the proportional assignment has makespan within a constant factor of optimum. So we know that there exist weights, we can predict those weights, we can use them to generate a fractional assignment, and then we can use the fractional assignment to generate an integer assignment, and all together we end up with a performance guarantee dependent on how effective our prediction mechanism is, that is sub-logarithmic, that beats the lower bound to that. So it really shows that, and if you know exactly, if I'm making exactly perfect weights, I get a log m cubed performance guarantee where otherwise log m was only achievable. So it shows the interplay between learning about the input and algorithm design. So I want to just give one hint of one more example of a recent result of Gaitonde Tardos, which, while the previous results build on the tradition of worst case analysis and competitive analysis and approximation, much more builds in the same sense of trying to adapt to a world in which multiple agents are distributed and competing for resources in the world of stochastic scheduling, in the world of queuing, and also highlights the interplay of building on recent work in learning in games. And in one of the sort of translations of approximation to the world of algorithmic game theory has been this notion of the price of anarchy, sort of how much the lack of control yields in terms of a performance guarantee in performance of the distributed setting rather than a centralized controlled one. And here, what I want you to think about is a setting in which we have routers that are competing for servers, and they're going to compete in rounds. And so as depicted in this picture here, you can think I have a set of queues that are each trying to get service at a collection of servers. Learning in games very much had the tradition overall dating back to really to the 50s, that as I think about playing repeated games, that each play was independent. But in a setting like this, the plays are not independent. If I, as a queue, try to get my packet shipped through a server, if I get a return message saying packet was not delivered, I'm going to want to resend that message in a subsequent time set. And so we have now no longer independent games that are playing in series, but rather a sequence of dependent games. So here's the basic setting that was considered by Gaitonde and Tardos. Each queue, QI, gets a new packet with a Bernoulli process arrival rate of lambda I. Server J succeeds in serving a particular packet with rate mu J. And at each time step, each queue can send one packet to one of the servers to try to get serviced. So there's this learning dynamic of what it's going to do. The server will look at all the incoming traffic and process at most one of them and return all of the ones that it doesn't get to process. The queues are going to function as what are often called no regret learning, too long to go into in the highlight of this time. And the main result is that, again, similar to the price of anarchy, if the servers have sufficient capacity, twice the total arrival rate, and the queues do use this no regret learning, then you can prove that the queue length at each server stays bounded in expectation. So again, this is blending many traditions of stochastic scheduling, learning in games, and trying to address the scheduling problems of the next decade of trying to manage the traffic in a distributed setting. So I hope I've given you a few examples of how new models are needed for data-driven decision-making. For example, in the last one, we're starting with a stylized model in terms of what the arrival rates and the service rates are. But of course, those are also values that can be learned over time. I believe that there's an important, exciting interplay with machine learning that's giving rise to these new challenges that will be a source of interesting problems informed by the real world. And as a consequence, we're seeing new bridges between the deterministic scheduling world and the stochastic scheduling world being formed. And once again, with the new applications, there are new opportunities for theory to guide practice and also learn and be informed in the models that it selects by practice itself. And with that, Jan-Carl and I are both happy to take questions. And please ask him the questions because you want to know more about the history.
No.
So nobody is asking questions on Slido, so I will now allow you to unmute. And if you would like to ask questions in person, then you can do it, okay?
And I guess before we start questions, if people haven't seen in the chat Gerhard's comment, I was shaking my head no as Jan-Carl made the statement that Christofides and Sverdukov have been beaten now in a really exciting result out of the University of Washington. And the archive paper is posted in the chat.
So beaten by how much?
Oh, don't ask.
Sorry?
Don't ask.
Well, I said it is essentially the best we can do, right?
True, you did say that.
Gerhard, say something so that we see that it works.
Yeah, so I think it's 10 to the minus 6 or something like this. So it's a
Oh yes, okay.
From...
Correction was the wrong word. Was refined. That's.
Anyhow, thank you, Gerhard. Good to see you.
All right, so questions. Nobody asking anything, so that's my role to ask at least something. So Jan Karel, could you advise me a good PhD topic for my PhD students? What would you choose, like one interesting one?
Don't choose a random problem from alpha, beta, gamma.
Something that is easy to
try to understand what David said in the last half of the talk and pursue that, because that is the interplay between practice and theory, and that is kind of what I said. It's way beyond my comprehension. It's the kind of stuff I didn't follow, but that's the good work is going on there. What do you think, David, for a PhD topic?
Gee, I think there are lots of, I do think that this, as I already promoted, I think this interplay of trying to understand interesting online models where we don't have satisfying theoretical results, either because from the stochastic side we feel that the distributions that we can analyze are not capturing the settings that practice cares about, or that the online analysis is too pessimistic, and to try to understand what might be the right kind of elements of the model that one can predict that would actually then allow us to, as a function of the prediction quality, allow us to derive better guarantees. But also, my fundamental belief is that the reason that we study theoretical models is to gain enough structural insight that actually allow us to derive better algorithms, and better algorithms in terms of how they work in practice. And in some sense, the theorem is somehow a proof to ourselves that we've learned something about the problem. Now, we all know, and I've been amongst that we can abuse such things and prove theorems that are nice theorems in and of themselves, that are maybe existence proofs of good algorithms, but are not really the things that you would actually want to use in practice. And as I've aged, I've certainly come more to the belief that the interplay between the two is just fundamental.
Okay.
If I may add a bit, the thing I said about local search and other methods being used in practice, that is not so easy, because the algorithms that we can analyze are pretty simple and don't work that well, and the methods that we use are too hard to analyze. But there are some advances in analyzing practical methods like local search and branch and bound. And I recently heard a talk by Daniel Tardos about this, which was very nice. And there are results on the performance analysis of local search. Perhaps not for scheduling, but certainly for the TSP there is something, for finding path of length 2 in a graph there is something. And there is a beginning of understanding of the behavior of the methods that are being used in practice. It's not easy.
Okay, so we can follow with one question, which is in the chat here. So how do you predict the future of machine learning and scheduling? So this is very up-to-date topic. So is it inevitable to study the machine learning? So probably somebody which is under the pressure of AI community.
I think that we don't understand. What is the role of us as theoreticians? The role of theoreticians is to provide an understanding for things that seem to work well, even though we don't understand them. And there's no question that in many settings, machine learning is providing power in a range, and I'm using machine learning in a very generic global sense, that is providing insight into how we solve decision-making problems. Whether it is simply a prediction role or whether it is a decision-making role, this varies from setting to setting. But this has been incorporated into the real world. And I think sort of thinking about how we can incorporate it in models and show how that we can design algorithms to make better decisions as a function of them is really an important aspect of ongoing research.
Yeah, I agree. I think it is imperative to study AI-based methods because we have to account for their way of operation rather than being baffled by our lack of understanding.
And indeed, the comment in the Slido about Tim Roughgarden is I highly recommend their recent book on beyond worst case analysis, because this is exactly trying to encapsulate ways in which we can push the standard models and advance things in surprising ways.
Okay, so could you go on with the question on Slido? I think you should have seen it. Huh? I'm sharing the screen, right?
I am not the person to answer this question. That's
I'm sorry. I have no opinion there. I don't know what Industry 4.0 is. I'm sorry, Mike. Mike, can you say something here?
Let me say something about where I think that scheduling in the future of job shops, and not also in the future of cloud computing, because there is a lot of scheduling going on in cloud computing. We have to look, and maybe, Jan-Karel, I'm going a little bit against you, that we should not look at random versions of alpha, beta, gamma problems, but I think that we should look at distribution functions, and maybe more Harkal, Walter will comment on this also, the distribution functions that have some tail heaviness, because they can screw up schedules. And it depends actually on the heaviness of the tail. First of all, then it makes predictability much more difficult. And machine learning becomes also more difficult because, when do we expect one of those outliers to hit us? And how robust should we build the schedule, knowing that something big can come up with a certain probability? And I think that is an area that has not been, that is actually of practical relevance. Maybe I'm completely biased, and maybe more is going to tell me that I'm full of it, and I want to hear this.
I'm going to agree with you, Mike. I'm totally agreeing with you.
Oh, you're so diplomatic. I think that we should look at that area of, very random processing times. How is machine learning dealing with that? And how are we going to create robust schedules that sort of will minimize disastrous impacts? Okay, that's my opinion. I'm curious what more is gonna. I would actually like it if she disagrees with me, because that.
I would just add something to what you're saying. So people are talking about how machine learning is going to help in scheduling, and that's certainly an area that one can look into. That's certainly important, but we also have a responsibility in the scheduling community of helping to schedule machine learning jobs. So machine learning jobs are actually those jobs that tend to be very, very long running. They're big training jobs. They're very parallel jobs. They use up a lot of the resources. In fact, they use up probably 99% of the resources in most data centers right now. It's our job to figure out how are we supposed to schedule those jobs, when to run them, how many cores to give them, and how many cores to take away from everybody else. And when to stop the training, when is the training done? There are a lot of questions there. So there's a lot of research opportunities, in my opinion, in that space.
All right, so do you have any more questions? So if not, then I will close the session. So you have the last opportunity to ask questions, or to send bottles of champagne to speakers, for example. Oh, now we are. So scheduling is a pretty hard problem. What do you think about using quantum computing to solve scheduling problems? Oh, does anybody has any idea about how to use quantum computing, specifically in scheduling problems?
I would say first build a quantum computer and then try to use quantum computing. It hasn't given so much to us in practice so far, yeah, I don't know.
I've learned to, I mean, I also said was equally skeptical about the strength of neural nets or their antecedents. So, you know, that I wouldn't say that it doesn't make sense to think about quantum algorithms for scheduling models. And it would be interesting to, I mean, it is a holy grail to show an NP-complete problem for which one can have a provable polynomial time. And, you know, is QP equal to QNP? And, you know, at least to my best of understanding that is still open. Even if something like factoring is solvable in quantum polynomial time. So, I mean, I wouldn't say, you know, that one shouldn't think about it, but you know, it's part of a broader agenda of understanding the power of quantum computing. It can be done in the context of scheduling, or it could be in the context of any other NP-complete problem. But you know, that's the beauty of reducibility. It says that you can choose your NP-complete problem as you wish.
But my impression is that theoretically there is not yet so much as the physicists want us to accept when they do this research, right?
Yeah, I mean, the building a large scale, you know, large. I mean, you know, even hundreds of qubit computer is something that is still only gradually taking shape.
Yeah.
My question is to that, if you have any idea, is are there some algorithms that are a little bit better suited to be run efficiently on quantum computing? For example, local search or genetic algorithms or branch and bound, or is it only about degree of parallelism that we can have in the algorithm, or is there some other aspect which is also like important?
I must confess complete ignorance. That I mean, I've gone to many talks on quantum algorithms, but I do not have an insight into how to think about what it means to live in this world of quantum, quantum computing. So it is a different mindset to thinking about algorithms, period. And as far as I can understand.
So it looks like a good PhD topic then.
It is a risky.
Yeah, risky, very risky.
Yeah.
Okay, there is another question, if you can read it.
Let me give a first crack at an answer here. If we replace that knowledge, representation, and reasoning versus AI planning, it is at the moment we know that our experience with constrained programming is that for many scheduling problems, it beats integer programming enormously, time-wise. You should listen to a talk by Pascal van Hentenrijk from Georgia Tech, and he will tell you that everybody who is working on integer programming is wasting his time. You should be working on constraint programming. Now, it is that those systems, there have been systems, actually a number of companies, tends to be smaller companies, are working in practice that are really not doing much integer programming and are really working with constraint propagation and knowledge representation, constraint propagation, etc., etc. I would say there are certain companies, and now it's one of the subsidiaries of Boeing, actually. They have a number of people that work. How does the hybrid work in practice? Integer programming and constraint programming. So you have an NP-complete problem of a certain size. Let's say the parameters are in the thousands or 10,000s, and you want to attack it, and that it becomes a trade-off with accuracy and computer time. And that trade-off between accuracy and computer time, the best approach will be some hybrid of integer programming and constraint programming. And how are you going to organize the system. And I think that there are some people in industry, not so much in academia, I think, or maybe the exception would be Pascal van Hentenrijk, that have some experience of how to attack industrial problems. I read what they're doing, but I don't have that experience.
But I wouldn't actually view it as such a dichotomy between thinking about the constrained programming aspect from the traditional optimization tools. If you look at, for example, the work of my soon-to-be colleague, Andrea Lodi, that really the integration in exactly the kind of learning that comes out of constrained programming within an optimization framework, again, has enormous potential. If you know where, if you can learn what kinds of cuts to add, if you can learn what, better branching rules in different settings through any number of knowledge representation approaches, this gives you better solvers. And certainly, Andrea is someone who has the industrial experience and the kudos in achievements in that dimension to show the benefits of nascent efforts in that direction.
Yeah, but I think there is still a difference between the integer programmers. Usually they have an objective function. The constraint programmers, they go for feasibility, and maybe there is some optimization in the back of their mind, not that strongly actually. And now in industry, some industry people really want optimization, but some industries really just want a feasible schedule, because actually it's very hard to find any feasible schedule. And then it becomes that. So I agree with you, it's not a dichotomy, and it's actually a continuous between two extremes. Yeah. And where are you gonna, whenever you build your system, where should you put yourself on that line between the two extremes, integer versus constraint, or optimal solution versus just a plain feasible solution? And that I think requires some experience and depends very, very much on the particular application.
Okay, thank you. And we have, I think, one of the last questions, if there are not other. Do you think deep reinforcement learning can be a good candidate approach to solve scheduling problems with stochastic demands? So it maybe goes to you, David.
Yeah, I think it would be, as long as I don't have to quantify what the words can be, it's certainly amongst the directions that are being explored and should be explored. And it would be good to, there's a question of, what does the words, solve mean? That it would, one thing to actually get good results in practice, and another to, provide an understanding mathematical foundation for knowing why the results that you're getting are happening. And it's a tremendously active line of research, not just with respect to scheduling, but a range of optimization problems. So definitely, I think there's an interesting work to be done there.
Oh, one more question.
I don't know of any.
I don't know.
No theorem proving match with us, right? Okay, so the last call, questions. None. So I think we have spent quite efficient 69 minutes, right? So yeah, especially in this COVID times where we cannot meet in person. So thank you, Jan Karel and David for speaking, and thanks to all other people. There were about 250 people attending the seminar. Maybe some of them have slept, we don't know, but maybe they have listened. And I hope that it will trigger interest for the next talk. which will be given by Mor Harchor-Balter, which is here, right, with us, and it will be given in 2 weeks at the same time, right? So thank you for coming, and if you do not object within, let's say, a few seconds, I will close the meeting, right?
Thank you, Zdenek and Mike and Guohua for organizing.
Thank you for both
Great pleasure.
speakers.
Thank you very much.
Thank
It
you
was
all.
great to at least see remotely or their names on a screen many colleagues that I have not seen for years. So it was really
Yes,
wonderful.
right. Yes, great.
That's it.
Great.
Okay, thank you.
Okay,
Bye.
see you in 2
Bye-bye.
weeks.
Thank you all. Thank you. Bye.
Nice to
Thank
meet
you. Bye-bye.
Bye-bye.
Bye-bye. See you next time.
Bye-bye.
Bye-bye.
Here.
Bye-bye.
Bye-bye. It was nice to meet you. Thank you. Bye-bye.
Bye again.
Bye-bye.
Bye-bye, Dave. Bye-bye, Dave.
Bye-bye, everybody. Bye-bye.
Oh.
All right, so I'm going to end it, right?
Okay.
Bye-bye.
Okay.
Bye-bye.
Okay, Zdenek. See you. Bye-bye.
Okay.